Two of the most fundamental and ubiquitous reactions in organic chemistry are substitution and elimination reactions. Today, we will be going over Sn2, E2, Sn1, and E1 mechanisms, and how to predict the major mechanism in products given solvent conditions. With that, let's begin.
We'll begin with the Sn2 reaction. In this mechanism, an electron-rich nucleophile selectively attacks the positive or partial positive charge of an atom to displace a leaving group from the same atom in a concerted manner, meaning that this entire process occurs in one step. Since two species are involved in the rate-determining step, this leads to the term substitution nucleophilic biomolecular, which is what Sn2 stands for, respectively. These reactions require a good nucleophile, such as sodium methoxide or potassium cyanide, and is preferable in various conditions that we'll describe later. So, how do Sn2 reactions work? The reaction most often occurs at an sp3 hybridized carbon with an electronegative stable leaving group attached to it. The breaking of the bond between this carbon and the leaving group and the formation of the new bond occur in one step through a transition state in which the carbon under nucleophilic attack is approximately sp2 hybridized. What's really important is that the nucleophile attacks the carbon with backside attack. This means 180 degrees to the leaving group, which provides the best overlap between the nucleophile's lone pair and the antibonding orbital of the carbon leaving group bond. The leaving group is then pushed off the opposite side, and the product is formed with inversion of stereochemistry. This backside attack is significant because Sn2 reactions only occur if the backside route is not sterically hindered by substituents on the substrate. If there is steric crowding on the substrate near the leaving group, the substitution will involve an Sn1 mechanism, which we'll get into later. In this reaction, the cyanide ion, a strong nucleophile, displaces the bromine from 2-bromobutane in a concerted mechanism with backside attack. The product that is formed has inversion of stereochemistry, with the nucleophile attached to the opposite side of that of the leaving group. Many factors affect the rate of this reaction, including substrate, nucleophile, solvent, and leaving group. The substrate plays the most important part in determining the rate of the reaction. As we've already said, to maximize the rate of the Sn2 reaction, the back of the substrate must be as unhindered as possible. Overall, this means that methyl and primary substrates react the fastest, followed by secondary substrates. Tertiary substrates don't participate in Sn2 reactions because of steric hindrance. Like the substrate, steric hindrance affects the nucleophile strength. The methoxide anion, for example, is both a strong base and nucleophile because it is a methyl nucleophile and is thus very much unhindered. Terbutoxide, on the other hand, is a strong base but a poor nucleophile because of its 3 methyl groups hindering its approach to the carbon. Nucleophile strength is also affected by charge and electronegativity. Nucleophilicity increases with increasing negative charge and decreasing electronegativity. But the solvent in which the reaction occurs also plays a role. The solvent affects the rate of reaction because solvents may hinder a nucleophile's approach to the carbon atom. Polar aprotic solvents, such as dimethyl sulfide and acetone, are better solvents for this reaction than polar protic solvents are, because polar protic solvents will hydrogen bond to the nucleophile if possible, hindering it from attacking the carbon with the leaving group. The stability of the leaving group as an anion and the strength of its bind to the carbon atom both affect the rate of reaction. The more stable the conjugate base of the leaving group is, the more likely that it'll take the 2 electrons of its bond to carbon during the reaction. Therefore, the weaker the leaving group is as a conjugate base, and thus the stronger its corresponding acid, the better the leaving group. Examples of good leaving groups are therefore the halides, except fluoride due to its strong bond to the carbon atom, and tosylate, whereas, for example, hydroxide is not.
Now, let's move on to E2 reactions. In E2 reactions, what essentially happens is that a strong base like sodium methoxide or potassium terbutoxide binds to a beta hydrogen and causes a double bond to form, which then results in a leaving group to leave. This process is a concerted reaction, meaning that everything happens in a single step. For E2 reactions to occur, you need 2 crucial ingredients. One is that it needs a strong base. A strong base is most commonly a negative charged molecule with a highly electronegative atom, such as oxygen, sulfur, or nitrogen. Second is that the hydrocarbon needs to have beta hydrogens, or else the reaction cannot occur. Now, if we examine one simple example, you can see that in this reaction, the tribute oxide binds to the hydrogen, which then donates the bond to form a double bond. And then at the end, you have an alkene with tributanol and iodide as the products. Now, keep in mind that the E2 reactions are in competition with Sn2 reactions. Usually, E2 has a higher activation energy, so normally it really only occurs when Sn2 is disfavored. Well, when would that be? Let's review. When is Sn2 disfavored? We know that Sn2 is disfavored when there's a lot of steric hindrance. The more extensively substituted a hydrocarbon is, the less likely that an Sn2 reaction is going to occur. In fact, for tertiary hydrocarbons, it's almost certain that E2 is preferred. Quick tip: if you see a quaternary carbon anywhere in the molecule, in the hydrocarbon or in the base, E2 is most likely the reaction that's going to occur. Also, if there's heat in the equation, it's more likely E2. There's just a couple of other things to keep in mind before we move on. E2 reactions occur by anti-addition, meaning that the beta hydrogen in the leaving group must be trans. In cases where there are many possible beta hydrogens, and therefore many different resulting alkenes, you should consider which alkene would be most stable. In case you don't remember, an alkene with more substituted alkyl groups at the double bond are the most stable. For example, let's examine the following reaction. The possible E2 products are the two shown below. The left one has 2 alkyl groups at the double bond, while the right one has 3. If you don't know how these two products have been formed, I suggest that you pause the video and take one more look at the explanation before we move on. So back to the problem. The right one has more alkyl substituents at the double bond, and therefore it is the most stable product. Got it? Alright, let's move on.
Now, what if you don't have a good nucleophile, but your substrate is in a polar protic solvent? In this case, your substrate molecule can react with the solvent in a reaction called solvolysis. There are 2 types of reactions where you don't directly add a good nucleophile or base: Sn1, which stands for substitution, nucleophilic, unimolecular, and E1, which stands for elimination, unimolecular. Now let's take a look at an example. For both Sn1 and E1 reactions, the rate-limiting step is the first step, where the molecule undergoes a Lewis acid-base dissociation to form a carbocation and ion. This is also why you need a polar protic solvent in Sn1 and E1 reactions, contrary to the preference of polar aprotic solvents in Sn2 and E2 reactions. Because the rate-limiting step only involves one molecule, Sn1 and E1 reactions are first order. Now, before going further, remember that carbocations are a warning signal for rearrangements, so make sure to consider methyl or hydride shifts that could turn the carbocation more stable, like, for example, secondary to tertiary. Speaking of carbocation stability, remember that primary carbocations are highly disfavored and very unstable, so a molecule that would become a primary carbocation after the dissociation step would typically not undergo Sn1 or E1 reactions. After the carbocation is formed, the Sn1 and E1 pathways compete in the product determining steps, and very often a mixture of products are formed. Let's start with the Sn1 mechanism. The solvent, in this case ethanol, first bonds to the carbocation and becomes positively charged, before another solvent molecule neutralizes that positive charge by attacking the hydrogen bonded to the electrophilic atom, oxygen. Even though the solvent is not a strong nucleophile, the carbocation is an extremely strong acid that readily accepts electrons, so that is not an issue. Now let's transition to the E1 reaction by revisiting the same carbocation, tert-butyl carbocation. In this case, the solvent molecule acts as a base by attacking the beta hydrogen. The electrons from the bond between the attacked beta hydrogen and attached beta carbon are transferred to the carbocation, forming an alkene. Similar to E2 products, remember that the most stable alkenes have the most substitution at the double bond. Although Sn1 and E1 reactions do frequently occur together, there are cases where you want to choose one over the other. For example, if the solvent is a good nucleophile but weak base, such as hydrochloric acid, then Sn1 will dominate. In contrast, if the solvent is a good base but weak nucleophile, such as sulfuric acid, then E1 will dominate. The addition of heat is also a strong hint that the reaction is E1.